Good morning, students. Hope you are finished with your previous assignment that was assigned to you. Let us today start with the calculation of number of atoms that are present in a unit cell. So let us view this slide first. Calculation of number of atoms in a unit cell. So there are three cases which we'll be seeing. The first one is the primitive cubic unit cell. Second one is the face-centered cubic unit cell. And the third one is body-centered cubic unit cell. We'll be seeing the calculation of number of atoms in a unit cell under three cases. Primitive cubic unit cell, body-centered cubic unit cell, and face-centered cubic unit cell. So we have dealt with the primitive cubic unit cell in the last lecture. There I said that in primitive cubic unit cell, the number of atoms that are present per unit cell, they are 8 in number. So primitive cubic unit cell has atoms only at its 8 corners, right? And each atom at a corner is being shared between 8 adjacent unit cells. You can see in this diagram. You can see this diagram. This is a simple cubic unit cell that is being given to you. A simple cubic unit cell. This is the diagram of it. And you can see one constituent particle that is there in between, right? And that constituent particle is present at its corner, right? And this corner constituent particle is being shared by 8 other adjacent unit cells. 4 in the same layer and 4 either on the top or on the lower side. I'll show you in this diagram. Yes, this is a primitive cubic unit cell. You can see the A part of the diagram. It is a primitive cubic unit cell. That is the open structure of a primitive cubic unit cell, right? The B part of the structure, that is the space filling model structure of the cubic unit cell, the primitive cubic unit cell. And here in this diagram, you can see 1/8 part of a constituent particle just belongs to one unit cell there. So 1/8 of this part of the atom belongs to one unit cell there. So each atom at a corner, as I said, is being shared between 8 adjacent unit cell. Therefore, contribution by a particle on the corner of a unit cell equals to 1/8. And in all, since each cubic unit cell has 8 atoms on its corner, the total number of atoms in one unit cell is 8 into 1/8, which is equal to 1 atom. So remember in your mind, the number of atoms in a primitive cubic unit cell is equal to 1. Total number of atoms in primitive cubic unit cell is equal to 1. Let us come to the next part, that is body-centered cubic unit cell. So in a body-centered cubic unit cell, you can see, as I said, you can see this diagram, A part of the diagram. There, in addition to the constituent particles that are present at its 8 corners, one constituent particle is present at its body. One constituent particle, you can see this particle, one constituent particle is present at its body in addition to the constituent particles that are there at its 8 corners. This is the open structure of body-centered cubic unit cell. This one, second one, you can see this is a space filling structure of BCC cubic unit cell, and this is the actual portion of atoms that is belonging to one unit cell there. So as I said, a body-centered cubic unit cell has atoms on its corners as well as atom at its body center. So in a body-centered cubic unit cell, 8 corners into 1/8 per corner atom, that is 8 into 1/8 is equal to 1 atom, and one body center atom, that is also equal to 1 atom. So total number of atoms per unit cell, you can see here, is equal to 2. So in case of body centered cubic unit cell, the total number of atoms that are present per unit cell equals to 2. Remember in your mind, total number of atoms that are present in a BCC unit cell, body centered cubic unit cell, is equal to 2 there. Then let us come to the face-centered cubic unit cell. In a face-centered cubic unit cell, as I said, if you look at the diagram, the face-centered cubic unit cell, you can see that figure 1.11. This is an atom at face center of cubic unit cell. Actually, this is the diagram of face-centered cubic unit cell. I explained you in the last lecture there. Face-centered cubic unit cell contains 8 constituent particles at its corners. Other than constituent particles that are present at its corner, one constituent particle is present at the center of each face. So a cube has 6 faces. There are 6 constituent particles at the center of each face there. So this is the open chain structure of space filling model for face centered cubic unit cell there. And this is the actual portion of atoms that is belonging to that of one unit cell there. This is the C part, actual portion of atoms belonging to one unit cell. So here I would like to tell, if you look at this figure 1.11, here you see one constituent particle. This is one constituent particle is shared between 2 unit cells there. So 2 unit cells share one constituent particle. So the one unit cell 1/2 part of the constituent particle belongs to. So to one unit cell 1/2 part only is the part that is present in face centered unit cell. So you can see in a face-centered cubic unit cell, in addition to the constituent particles that are present at its 8 corners, 8 into 1/8 atoms per unit cell is equal to 1 atom. And since 6 faces are there and 1/2 is the contribution of atom per unit cell, it is 6 into 1/2 comes out to be 3 atoms there. So the total number of atoms that are present per unit cell in case of FCC, face centered cubic unit cell, is equal to 4. So the total number of atoms that are present per unit cell in case of FCC is equal to 4. Remember in your mind. I repeat once again, the total number of atoms that are present in primitive cubic unit cell is equal to 1. The total number of atoms that are present in case of body-centered cubic unit cells equals to 2, and the total number of atoms that are present in case of face-centered cubic unit cell is equal to 4 there. Now let us come to the closed pack structures. Before I deal with this closed pack structures, I would like to tell you about coordination number. Coordination number is the number of nearest neighbors of a particle. The number of nearest neighbors of a particle is called as a coordination number. I give you an example for it to explain. That is, suppose you are traveling in a train, right? And one person is sitting left to you and the other person is sitting right to you. So the total number of persons who are in contact with you are 2. So the coordination number is 2. Similarly, if a particle, constituent particle, is in contact with 2 other spheres there, its coordination number becomes equal to 2. So the coordination number is the number of nearest neighbors of a particle that are surrounding it. That is called as your coordination number. Here we'll be studying about closed pack structures in detail, about closed pack structures in 1 dimension, closed pack structures in 2 dimensions, and closed pack structures in 3 dimensions respectively there. So firstly we'll see the closed pack structure in 1 dimension there, closed packing in 1 dimension. So closed packing in 1 dimension can be done in this way, either by arranging, here we are considering the constituent particles to be spheres there, right? They are identical spheres which are in contact with one another. So we'll see this close packing of spheres in 1 dimensions. These particles can be arranged either horizontally as I'm showing you in this figure, or they can be also arranged vertically there. So here if you see, each constituent particle is in contact. Suppose I see the second sphere. This is in contact with 2 other spheres there. If you see the third sphere is also in contact with 2 other spheres there. So the coordination number of close packing of spheres in 1 dimension is equal to 2 there. right? So close packing in one dimension is very easy to understand. Either you can arrange the spheres horizontally or you can arrange vertically there. Let us come to the close packing in two dimensions there. So close packing in two dimensions, it can be done in two different ways. I'll show you the diagram. Close packing in two dimensions. Two-dimensional close packing can be generated by placing the rows of closed packed structures or spheres. That can be done in two different ways. The first way is to arrange AAA type of arrangement, and the second one is AB type of arrangement. I'll explain you with the help of this diagram. Close packing in two dimension. So if you look at this diagram, this is close packing in two dimension. You can see this is a sphere alignment. Suppose I take the first horizontal layer. This I name this pattern as A. Second also, the spheres I am arranging in the same way in the second row. I am arranging in the third way in the third row. I am arranging in the same way in the fourth row. That is, it is resulting in giving you AAA type of pattern there. So in AAA type of pattern, if you look at this particle, right? If you look at this particle is in contact with four other spheres. 1, 2, 3 and 4. This is in contact with four other spheres there. And if I join the midpoints of these four spheres, it results in giving me a square closed pack structure there. So AAA type of arrangement, that is close packing in two dimensions, when we arrange the spheres in AAA type of arrangement, it results in giving us a square closed pack structure. Whereas close packing in two dimension can be done in the other way also. Close packing in two dimensions. Here what we do, we fit these spheres. The first layer, suppose it is the B pattern there. I put the second layer, that is A layer, in the depressions of this first layer there. So I am fitting these spheres in the depressions of the first layer. So this becomes AB type of arrangement. So in case of AB type of arrangement, if you look at a constituent particle, suppose I take this constituent particle, this is in contact with 6 other spheres. 1, 2, 3, 4, 5 and 6. If I join the midpoints of these 6 spheres, it results in giving me a hexagonal closed pack structure there. So it results in giving you HCP type of arrangement. On joining the midpoint, 6 midpoints of these spheres, it results in giving you HCP type of structure. So close packing in two dimensions can be done in two ways. One is by putting AAA type of arrangement, in which AAA type of arrangement, when I join the midpoints of each, it results in giving me square closed pack structure. Whereas AB type of arrangement, it results in giving me a hexagonal cubic closed pack structure there, that is HCP structure. In this structure, AB type of arrangement, I am putting the layer, that is the second layer, I am putting in the depressions of the first layer there. So if you see, if the arrangement of spheres in the first row is A type, the other one, second row is different and it's called as B type. In this, the second row is placed over the first one in a staggered manner, such that its spheres fit in the depressions of the first row there. So it results in giving you two-dimensional hexagonal closed packing there. Let us come to the next type of arrangement, that is close packing in three dimensions there. So close packing in three dimensions, three-dimensional close packing from two-dimensional square closed pack structures. It is also done in two ways. First way is three-dimensional close packing from two-dimensional square closed pack structures. So while placing the second square closed packed layer over the first, we follow the same rule that was followed when one row was placed adjacent to one another. the second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer there. You can see in this diagram. So what I do, this is closed packing in 3 dimensions, that is from square closed pack structure. This was 2-dimensional shape which I showed you, and this diagram which I'm showing you, this I'm placing exactly the rows in the either vertically as well as horizontally. We are placing the spheres there, and it results in giving you a simple cubic lattice pattern there. So a type of arrangement is formed, resulting in giving you simple cubic lattice that is formed. So this is one way of arranging 3-dimensional layers by using 2-dimensional closed pack structure, that is square closed pack structure there. Let us come to the 3-dimensional closed packing from 2-dimensional closed pack structures, so that is hexagonal closed pack structures. This can be generated by placing layers one over the other there. That is, the first way is by placing second layer over the first layer. To understand this, let me show you a diagram here. Look at this diagram. This was solid lines. You can see solid spheres which are there. This was A type of pattern, and the second one is your B type of pattern, right? This was 2-dimensional shape that was shown. Now here I am putting another layer of it. Second layer I am placing over this. This is represented by this dotted lines. You can see the dotted lines. I am putting the second layer over this first layer there. So this type of arrangement leads to 2 types of voids. Voids are empty spaces, right? So this leads to 2 types of voids, you can see, and they are represented by T or they are represented by O there. So when 4 spheres come in contact with one another, you can see this is the solid sphere which I am considering 1. This is the second solid sphere which I am considering 2. This is the third solid sphere which I am considering 3. Right? Now I am placing a second layer over this first layer. 1, the dotted line, 2, and the 3. Right? This results in giving you this one, 2 types of voids, tetrahedral voids and octahedral voids. Tetrahedral voids are formed when 4 spheres come in contact with one another. Look at the solid spheres, 1, 2, 3, and this is the second layer which I am placing, right? And it results in giving you a tetrahedral void represented by T. And an octahedral void is formed when 6 spheres come in contact with one another. So you see this octahedral void. 6 spheres come in contact with one another there, right? So 6 spheres that come in contact with one another. You see the octahedral void. 1, 2, 3, and this is 4, 5, and 6. So see here, an octahedral void is formed. So there are 2 types of voids that are formed. One is tetrahedral void because of the formation of tetrahedron, and the octahedral void because of the formation of octahedron there. Tetrahedral voids, they are triangular voids that you will be seeing, and at other places the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap, in which one of them has the apex of the triangle pointing upwards, right, and the other pointing downwards, and so they are marked with O in this diagram, octahedral voids. They result in 2 types of voids, tetrahedral and octahedral voids. Look at this diagram, it is more clear. You can see here, when 4 spheres come in contact with one another, you can see 3 blue spheres and the fourth one, which is shown with the red one. It results in forming a tetrahedral hole, forming a tetrahedron, right? Similarly, this is the top view. if you see the second diagram, octahedral view, here 6 spheres come in contact with one another, and this results in the formation of an octahedral hole, forming an octahedron, right? So two types of voids are generated, and they result in the formation of tetrahedral and octahedral voids there. Now, with this, the concept that comes in is the number of these two types of voids depend upon the number of closed packed structures, right? So if the number of closed packed structures is represented by capital N, if the number of closed packed structures is represented by capital N, then the number of octahedral voids generated will also be equal to capital N. That is the number of closed packed spheres. And the number of tetrahedral voids that is generated will be double the number of closed packed structures, that is equal to 2n. Right? This concept should be very clear in your mind, that if the number of closed packed structures is equal to n, the number of octahedral voids that is generated is also equal to n, and the number of tetrahedral voids that will be generated is 2n, that double the number of closed packed structures. That is the concept which will be helpful for you for calculation in the formula there. Now let us come to the next slide, that is close packing in three-dimensional layer, that is placing third layer over the second layer. Here I placed second layer over the first layer. That was the first case. Second case will be seeing placing third layer over the second layer there. Placing third layer over the second layer. By this can be done in two different ways, by covering the tetrahedral voids, and the other one is by covering the octahedral voids there. So when I place a third layer over the second layer by covering the tetrahedral voids, it results, you can see, it results in AB type of pattern. Look at this diagram, figure 1.5, A part, right? This results in giving you hexagonal close packing there, AB type of arrangement. In AB type of arrangement, when I place the third layer over the second layer there, AB type of pattern, we are covering the tetrahedral voids here. It leads to hexagonal close packed structure. Look at this structure, AB type of structure. When I put a third layer, that is A over B, that is we are covering the tetrahedral void, that leads to the formation of hexagonal cubic close packed structure there. So this type, AB type of arrangement leads to the structure called hexagonal closed packed structure, and this sort of arrangement of atoms is found in metals like magnesium and zinc. So this sort of arrangement, that is HCP type of arrangement, is seen in metals like magnesium and zinc. Look at the next part, that is when I cover the octahedral voids there. So when I cover the octahedral voids by placing the third layer over the second layer, that is it leads to ABC type of pattern, ABC type of pattern. You can see this diagram here, the C part which is there, C part, here we are covering the octahedral void by placing this layer over it. So when I place this layer over this part, it ABC type of pattern, this leads to two types of structures. Either it gives CCP type of structure, that is cubic closed packed structure, or it leads to FCC type of structure, that is face centered cubic unit cell. So when I am covering the octahedral voids by putting the third layer over the second layer, and we are covering the octahedral voids, this leads to the pattern ABC type, giving rise to either FCC, that is face centered cubic unit cell, or CCP, cubic closed packed structure. You can see this in the diagram, ABC type of structure. When we are covering, it leads to the geometry either CCP type or it leads to FCC type of structures there. Look at this diagram, ABC type of arrangement of layers when octahedral void is covered, right? This figure you can see, this is octahedral void is been covered there, A. Here octahedral void is been covered, and this B part of the diagram is showing fragment of structure formed by this arrangement resulting in cubic closed pack structure, that is CCP type of structure or FCC structure there. Face centered cubic lattice structure is formed. So this is a figure which you have to imagine in your mind, which is a three-dimensional arrangement, and metals such as copper and silver crystallize in this structure, that is FCC or CCP type of arrangement. Pattern of layers is ABC type of structure. In this, examples which come under metals like copper and silver, they crystallize in this type of structure there, and the coordination number is 12 in either of these two spheres. I mean to say 12, coordination number is equal to 12 because the sphere which you are seeing, this is in contact with 12 other spheres there. So the coordination number in either of these structures is equal to 12. So I end up with my lecture here. In the next lecture, I would explain you how to calculate the formula of the compound. So till then, please read, be thorough with this part so that we can continue with the calculation of formulas in the next lecture. Thank you so much.